Hi everyone, my name is Terry and I'm going to be doing a presentation tonight on SRAM. SRAM stands for Static Random Access Memory. I'm sure we've all heard of RAM. We can find it every day in our computers, and most electronic devices now use some sort of RAM or memory storage. So static random access memory, it is a type of semiconductor memory that uses bistable latching circuitry to store each bit. It's named static because it will retain its values as long as there's power supplied to it. So if you have your computer on or you have your electronic device on and there's power to it, it'll store that data in the memory. But if your power goes out, then you will lose whatever was in that memory. Unlike DRAM, which needs to be refreshed regularly. So SRAM is usually much faster than DRAM, but since each bit of the SRAM requires several transistors, you can get less bits of SRAM in the same area as you would DRAM. And it usually costs more per bit than DRAM, and so it's only used in the most speed critical parts of a computer, so like the cache memory and other important parts of electronic devices. So on average, DRAM supports access times of around 60 nanoseconds, where SRAM supports access time as low as 10 nanoseconds. So you can see an obvious speed increase in SRAM versus DRAM. So let's talk about the types of SRAM there are. We have non-volatile. So non-volatile SRAMs, or NV-SRAMs, have standard SRAM functionality, but they save the data when the power supply is lost. So it ensures the preservation of all critical information. NV-SRAMs are used in a wide range of situations nowadays, especially with all the new technical and technological advances that we have, anywhere from networking to aerospace to medical devices, and tons of other things, where the preservation of data when something critical happens like a power outage, and where batteries just aren't practical in a situation. So we have bitransistor type. We have bipolar junction transistor. It's used in the TTL and ECL. It's very fast, but it consumes a lot of power. So we then have the MOSFET, which is used in standard CMOS. If anyone has ever seen a computer, you have CMOS, which has low power and very common in devices today. You'll see a lot, especially on motherboards, where you'll have the CMOS and CMOS battery. If you take that out, then it flashes. Other types. By function, asynchronous is independent of clock frequency. Data in and data out are controlled by address transition. Then you have synchronous. All timings are initiated by the clock edge address, and the data and other control signals are associated with the clock signals. Then we have by feature. ZBT stands for the zero bus turnaround. The turnaround is the number of clock cycles it takes to change the access to the SRAM from the write to the read and vice versa. So the turnaround for ZBT SRAMs, or latency between the read and write cycle, is 0. And as you can see, I do have some images of what SRAM circuits might look like and pictures of the SRAMs. Sync burst. Sync burst SRAM, or synchronous burst SRAM, features synchronous burst write access to the SRAM to increase the write operation to the SRAM. And then DDR SRAM, we have all heard of DDR. Synchronous single read-write port at a double data rate. So DDR, double data rate. And then synchronous single read-write port, double data rate I/O as well. We have the quad data rate SRAM. synchronous, separate read and write ports with a quadruple data rate on the I/O. And then by flip-flop, you have binary SRAM and ternary SRAM as well. SRAM operations. So we have standby. So if the word line is not asserted, the access transistors M5 and M6 disconnect the cell from the bit lines. The two cross-coupled inverters formed by M1 and M4 will continue to reinforce each other as long as they are connected to the supply. Reading. So in theory, when the reading process requires only asserting in the word line and reading the SRAM cell states by single access transistor and bit line, nevertheless, bit lines are relatively long with parasitic capacitance. Therefore, to speed up the reading, more complex process is used in practice. So the read cycle is started by pre-charging by an external both bit lines, BL and BL, i.e. driving the bit to the threshold voltage. So the mid-range voltage between 1 and 0. And then asserting the word line, enabling both the access transistors, the M5, M6, which causes the bit line voltage either slightly drops, bottom NMOS transistor M3 on, the top PMOS transistor M4 is off and rises. So very technical stuff in the reading. It should be noted that, if the BL rises, then the BL voltage drops and vice versa. So the BL lines have a small voltage difference between them while reaching a sense of amplifier, which will sense the higher voltage line, thus determining whether the one stored or 0. So the higher the sensitivity of the sense amplifier, the faster the speed of the read operation. So that's basically the nuts and bolts of the reading. That the higher the sensitivity of the sense amplifier, the faster the speed of the read operation is what we want to take away. And then we have the writing. The start of a write cycle begins by applying the value to be written to the bit line. If we wish to write a 0, we would apply a 0 to the bit lines, and then setting the bit line to 1 and the BL to 0. So this is similar to applying a reset pulse on an SR latch. Obviously, we've done the resets on our circuit designs in class, which causes the flip-flop to change state A. A1 is written, to change the state. A1 is written inverting the values to the bit lines. WL is then asserted, and the value that is stored is latched in. The reason that this works is that the bit line input drivers are designed to be much stronger than the relatively weak transistors in the cell itself, so they can easily override the previous state of the cross-coupled inverters. And a lot of the stuff that I'm talking about, if you're in our CSC 340 class, you may have used already, hopefully, because we're on the last weekend of a class, the inverters and the latches might sound familiar to you. So in practice, access NMOS transistors M5 and M6 have to be stronger than the bottom NMOS, M1 and M3, or top PMOS, M2 and M4 transistors. This is easily obtained by the PMOS transistors are much weaker than the NMOS when same sized. Consequently, when the transistors are paired, M3 and 4 is only slightly override by the write process. The opposite transistor pair, M1, M2, the gate voltage is also changed. So this causes that M1 and M2 transistors can be easily overridden and so on. Then the cross-coupled inverters magnify the writing process. So what are some of the typical uses for SRAM? Cache of a CPU. Obviously, when you're talking about something that has high calculation rates, there's CPUs out there doing trillions of calculations in milliseconds. So the memory you need to have stored would definitely be more beneficial to have SRAM instead of your normal DRAM. Digital processing circuits. Again, anything that has to process information that needs access to memory extremely fast, um, you're going to want something that has a faster access rate, read-write rate, especially if you're doing anything in the digital. I had something that would render in Photoshop that would take a very long time. So you can definitely speed the processing up if you have your SRAM, if you were to do it in SRAM. So SRAM for hobbyists, anybody who wants to get into electrical circuitry, designing motherboards, any other electronic devices that need to have memory stored and accessed extremely fast. Um, you can definitely do it for an everyday hobbyist. Myself, I'm horrible with circuits, so I would never want to waste the money on that. So another current role for SRAM is that it's very significantly easier to work with at a hobbyist level or an entry-level circuit builder like myself or any one of you in the class that this might be their first time designing something like this. It's much easier to work with on that type of a level than DRAM. For one, you don't have to deal with the refresh cycles of DRAM. And for historical reasons, the address and signal pins are separate rather than multiplexed. So the chip has a very straightforward pin in, pin out. Power ground, some address pins, some data pins, and 3 control pins. So you have write enable, chip enable, and output enable. Chip enable is there to allow systems containing multiple SRAM chips. You can use as a demultiplexer. Again, another word there, demultiplexer, that we should know from this class. Something like the S7 or 74LS154. If you are using multisim, you could look that up in multisim to convert upper bits of the address into chip enable for one of 16 chips. So here's a basic circuit design of what static RAM would look like. The flip-flop, if you follow along, you will see the NMOS and the PMOS and the flip-flop circuits and the constant voltage. This might look like something that we've seen in our class designs or our labs. You might see the grounds and the lead wires and everything like that, and the voltage line. And it may all look familiar to you. So that's the end of my presentation. Again, static random access memory, much, much faster than your normal DRAM. And I would assume that the way things are going is that we're going to see a lot more of this, especially as we start seeing things like, take for example, something I could think of is maybe a car driving by itself, the Google car, that needs to have data accessed extremely fast. So you might see it in there. Again, anything on a processing level, CPU usage, anything like that, you're going to find SRAM, because even though it's a little more expensive, again, if we go back, the DRAM is accessed at 60 nanoseconds, where the SRAM can be accessed at 10 nanoseconds. So if anyone has any questions or comments, I would love your feedback. Again, this is only I haven't done very many presentations in our classes so far, so any feedback would be great and appreciated. And again, if you have any questions or on the static random access memory, you can email me through our class, and I would love to give you some of the links I used and some of the some of the pages I've read on on this SRAM. It's extremely fascinating to see how much difference there are in the normal DRAM versus the SRAM. So I had a really fun time with this presentation. I'm glad I picked this topic because um, as a software engineer, I am using read write access all the time, and especially diving further into the computer science field, I think we're going to start seeing a lot more of this with the cycles. Um, and if you're a hobbyist and you want to get into something like this and use, the multisim tool outside of class, or using a breadboard or anything like that, or something definitely higher than that, this would be a lot of fun. So again, thank you. This is Terry. It's been a pleasure, and I will see you soon. Bye bye.